All right, say 495. Let's continue. So, where we are, we just build a 3D model of the one typical floor framing, right? This floor framing is relatively simple. I start out with the regular grid system, Control D, Control, but in reality, it's more complex. It depends on the building geometry, but obviously the same method you can apply, but I think sometimes you may end up to draw different way, maybe using sometimes the AutoCAD background DXF and put it as a background, and you can draw the column and beams, something like that. But if the building is a regular basis, and you can set it up grid, I think you most likely play with grid here. So once you have a nice grid setting, right, X and Y, I think it's pretty decently handle it. All right, so I think one thing I want to make sure that everybody just drawing the geometry is not engineering. To me, it's a basic of a basic. You should have some sense of just structure, right? And structural elements, including column, wall, and girder and beams, right? But assume that you complete it always. I said always, you need to check the forces. So based upon your input, Taylor, Live, whatever the case is, just check this moment diagram and shear force diagram. Obviously, beam is loaded on top on the slabs. All the major forces is going downward, generating the slab and beam deflection, right? Since beam is deflect, which means it's bent, so it generates the beams inside interior forces like shear and moment. So this is kind of physics. I'm sure everybody know it. And then we're gonna move on next. So once you confirm your model, because we are human, always make a mistake. You always double check, cross check deflection shape, moment and shear, and see every your input seems correct. So that you need to validate your all modeling, right? I'm just teaching these classes as part of the industrial kind of practice. So I hope everybody really get this and take it from here. All right. So the force is ready, building is ready. I'm gonna move on to design composite beam design. All right. So last time we set up the load combination by using this feature composite beam. So this is load combination. We're gonna use it when you run the composite beam design. Let's see. So go to design module, right? And we're gonna go to composite beam design. There is some preference. This is basic setting that for the composite beam design, we follow along some standardized our agreement, and eventually we are using sure start. I'm gonna show you later, because composite beam, I think the concrete and steel should be tied together, which means glued together. So those beam work like a T beam. It's similar to the concrete. So typically beam is bending member on against the uniform loading. The top of the beam will experience compression, bottom of a beam experiencing tension. Since we tie together, most of compression stress will develop in the slab and some tension in the bottom side of the beam. So that's why we can maximize the strength and stiffness by using this composite action. All right, so there is some setting we're gonna talk about later, and also camber. I'm gonna show you later what is camber and deflection criteria and vibration criteria. So this is just general AISC 360 setting, right? So that is setting, and go to design on composite beam and select group. Okay, we're gonna just run. We don't want to group it. So every single beams we're gonna design and so that ETABS will choose right workable section size for each the beam and girder. And combination, yes, since we follow using ETABS combination, they distribute it. So C1, C2, it's part of construction design phases. S1 and S2 is part of strength permanent conditions. And also deflection check, they're using service load combination, right? So I want you to just go through and see. I'm sure most of you guys some thought of experience in the steel class. So basically, we check for the strength at the construction phase and strength phase. So construction phase is obvious, as I said, construction phase when metal deck or steel beam and the column and steel beam and girder is placed, and then metal deck is placed on top of the beams, and then concrete is wet concrete when we pour the concrete, right? Still, the concrete is before the concrete get hardened. This beam and deck is running, supporting all the weight. So that state we call construction phase. The steel beam should carry and the weight, wet concrete weight. So that is a phase that we need to check the strength and deflection at that phase. After concrete is cured, is fully cured, is developed the composite action. So the beam and slab is fully quite compositely glued together. Then the stiffness and strength is really much higher, so that we is more using benefit of composite action for permanent beam design. Deflection check, yes, deflection check is also important. So this is part of serviceability. You know that, right? L over 360 under live road. Those something that during the design phases, ETABS will calculate and check it. All right, so let's run the composite beam here. All right, so let's put this one on the plan view. So first run the ETABS and show some recommending the beam sizes. Since 45 feet long, right click, we'll choose one typical beam. You see, in the auto selection groups, they showed all the beam is walkable, right? W21 by 50 and number of stud 39, also using 2-inch camber. Their stress level 0.999. Okay, so obviously heavier beams, we end up with a lower stress level. So common sense. So this is something ETABS will calculate and propose that what beam is working for this condition. And on the right side, you see that strength check calculation summary and constructability deflection check summaries are there. You need to understand all this. Basically, same the whatever just factor load, right, for the bending, right, for construction bending, construction phase, and permanent cases, load combination. ETABS calculate load bending moment here, and design check, which is the bending capacity. The construction bending, basically here capacity is always provided by the steel section, right? Steel beam is fully supporting the wet concrete, so their design capacity is much lower. But here the two full composite bending and partial composite bending, they provided two, but since they proposed number of studs 39, we only develop 55% of composite action. So it's end up to our bending capacity 781, right? So obviously, if this is maybe intentionally we increase to 100, let's say. If we include this increase intentionally the composite action, the capacity increase, right? What was that before? Yeah, he proposed 55, something like that, right? So this full capacity bending is based upon their full capacity, which means the concrete and beam is fully glued together, so that there can reach full composite action effect but it's totally depends on number of studs. More studs will develop more full capacity. So here 55%, so we only get the partial composite bending capacity, so 781. Still our factor maximum bending moment is only 714, so we are okay, right? So this is bending check. And on the bottom there is a deflection check. So here pre-composite action is, I think, deflection. So that this is, I think, construction phase. The beam, whatever they select, let's for example W21 by 50, will be deflect under weight of concrete as much as 2.6 inches, right? So it's not, this case is construction phase. They are checking the deflection, the beam deflection under the concrete weight, which 2.6 is quite significant, right? But after concrete is cured, we call post composite action, right? This deflection is much lower, right? Because the stiffness is bigger. So this is post composite deflection. We better double check. But after concrete is cured, then the SDL superimposed dead load and live load is applied. So typically, post composite action deflection include the composite beam deflection under the superimposed dead load and live load. So live load deflection load, yes, obviously a little bit similar because this is live load deflection for the composite beam. So this live load deflection is slightly smaller. So live load deflection criteria L over 360, which means 45 feet times 12 divided by 360, you get into this 1.5 inches. Let's say 45 times 12 divided by 360. Yeah, 1.5 inches. All right. But because of substantial the beam deflection under the construction phase, we sometimes use a camber. Most commonly use camber, so that in the during the fabrication of the beam, we just beam is camber up, bend up by here. How many inches? Point here camber 2 inches. So we try to, when the concrete is loaded, right, wet concrete loaded, beam is kind of leveling to flat, so that many cases long span beam with a high heavy dead load, we ETABS or engineering our practice, we using camber. So those are all the calculation you need to get used to. This is hard of composite beam and steel floor framing construction and calculations. And I didn't expect vibration yet, but I want you to take a look at it. I'm sure you could follow along some of them based upon your steel class. And this, if you click the report, you'll see all the summary of calculation. The one thing I'm make it clear, I want you to memorize it, understand fully. Because of this composite beam, all deflection calculation, you should refer to this calculation here. Okay, so all this calculation here, deflection, live load deflection, or post composite beam deflection, you should always look at this calculation platform, right? Otherwise, for example, here in when you run the 3D model, put it in 3D, you're checking the deflection here. Let's say live load deflection here, right? I'm gonna turn up the slab floor, right? This beam deflection, Control D. So let's say this, and if you click this beam, you know what? Let's click to show the moment. Click the beam. So here, when you look at the deformation shape from deflection here, see that deflection at 4.3 inches. This is pure steel deflection under the live rod, right? Which it doesn't the ETABS at this mode doesn't consider composite action. So deflection under the live load is much bigger because in this analysis, ETABS is only count for the steel to calculate the live load deflection. I said every student they confuse, they only summarize this and present this beam live load deflection by using this screen, which is not right. So I want to make sure that you just look through it and properly address your beam design calculation. Okay, so we're not looking at this beam deflections. This is pure steel beam deflection here. The only deflection when you checking, you need to run composite beam again. Vertical, yeah, right. And the right click here, you should look at the beam deflection here. So live load beam deflection, because it's a composite action under permanent condition, your live load deflection will be the 0.97 inches instead of 4.6. Okay, so I'm gonna stop here for composite beam design. So I want you to also practice this, and I would like to, this is part of homework, everybody actually worked on it, and submit your first trial 3D ETABS framing build up and do the composite beam design and present your homework to me. All right.